Hey, hello, welcome everyone. Thanks for attending this talk. My name is Oscar Celma, and today I would like to present some work we've been doing at Pandora, how to combine machine learning and AI and put the humans or the experts in this loop. So I've been at Pandora for almost 3.5 years. I'm the head of research, so I manage a team of almost 80 people, 40 scientists that come from like PhDs in computer science and electrical engineering and astrophysics, but also I manage the team that does the Music Genome Project. That's kind of the core, or what Pandora is well known for. So we've been annotating music for the last 17 years or 18 years now. And I have this music annotated with this catalog of music that no one else in the world has. So these experts or musicologists that listen to music one song at a time and annotate them, they also report to me. And then my goal is to combine, the expertise of all these musicologists with the science and the research that the other half of the team work on. So let's start then. Before we go into the meaty part of the presentation, I would like to give a brief introduction. That will be quick. So what's Pandora? Or Pandora vision is to be the effortless source of personalized music enjoyment and discovery. So my team, which is kind of the core part at Pandora that builds the algorithms, the way we decide which song to play for you. Once you thumb down a song or skip a song, we need to quickly decide what to play next for you. So my team is the one that really tries to fulfill this mission of playing music that you will like and also discover and enhance your music horizons. So Pandora, we have 3 tiers or 3 different type of Pandoras. The ad-supported one, where you can create stations and personalize them. You create the Poses radio, and then you can start listening and enjoying this music with some ads in between some songs. So that's the ad-supported model, and you can personalize them by providing feedback. But also, so you can create stations, but also you can see on the browse where we can also personalize and bring you content that the music experts, the curators have created. So we can also personalize and bring content to you. In this case, like based on my music tastes, the algorithm or the machine learning part that decided to recommend me this indie rock curated station or some jazz stations. So that's kind of the basic Pandora. Then we have what is called Pandora Plus, which is a mid-tier, $5 a month, where you have no ads, but also you have more skips. So you can click on these buttons more often and than the ad-supported one. And also we offer the offline mode, where you can listen to some stations in offline mode whilst flying, and also has the replay button. So it's kind of a pseudo-on-demand version where you can listen to the songs we personalize for you, songs that we think you might like, but also you can replay them, you can skip more often, you have no ads. So that's kind of the second Pandora tier. And last but not least, we recently, mid-March, we released the Pandora Premium, kind of the on-demand, similar to the other services available, where you can create playlists, you can listen to all the songs that you want, you can listen to full albums. So that's kind of the 3 tiers that we have at Pandora. And today I will focus mainly on how can we personalize and how can we leverage the human expertise to tailor and bring you content to you. I'm almost done with introduction. So in terms of some numbers here, we have 76 million active users, monthly active users at Pandora. They spend almost 1 day, full day with us per month. And we also embedded into a lot of consumer electronics and automotive. We're really strong on embedding into CE and auto. In terms of the collection and the size, we have, of course, millions and millions of songs, most of them annotated by experts. Something that we're especially proud or happy at the radio version of Pandora is that every month we play almost the whole catalog, or most of the artists that are at Pandora, they're played in radio mode every month. And that's something that's very uncommon in other places or other services, because what we're trying to do is also promote the long tail and more unknown music, and the ones that we think you might like try to spin, play some music for you every now and then. In terms of data, like especially for machine learning engineers and scientists, they are really excited to work with 80 billion thumbs. So we've been collecting a lot of data from all our users, and also they've created like over 11 billion stations. So you can imagine a lot of, for the more techy people in the audience, like correlative filtering or some ways to decide that people that create this station also create these other stations, or people that thumb up Adele also thumb up Amy Winehouse. So you can create a lot of similarities and extract a lot of meaningful data out of this huge amount of data that we get daily. That's it then. Let's focus how can we add the human in the loop, or what we call the magic formula at Pandora, where we combine the algorithms and the machine learning, and we also embed or leverage all the human knowledge. So the rest of the presentation I'll focus mainly on this thing, the magic formula, which actually doesn't make that much sense, but the idea is that I'll talk about how we curate music, how we analyze music, how can we leverage all this with algorithms to scale and personalize to our user base, and then that's what it makes Pandora so special. So the rest of the presentation, I'll focus on these three aspects: the music curation, music analysis, and algorithms, and the combination of the three of them. So let's start with music curation. So curators are music experts that they keep our catalog up to date, that they clean. There's a lot of metadata issues, so they are the ones that really try to have a clean and organized music collection. Specifically, we got a lot of content weekly. We get like thousands of releases every Friday that we need to process. Of course, humans cannot process them all. So what we have here is the ingestion process. Music mainly comes from labels and approved labels and artists, like the famous ones, but also we offer submissions for independent artists that are unsigned or they don't have any contract with the record labels. What we do is that they also can submit their music, so the music curators will listen to everything that's submitted to us and then decide if it's a good fit for radio or not, and then ingest it into our catalog. We also have what we call radars, where we have a company, actually part of Pandora now. We acquired a company called Next Big Sound a couple of years ago. They're mining and constantly mining the web, like the YouTube and Facebook, Twitter, etc., where we get all these signals about artists that potentially become big, but also we're trending. We're not only trending and seeing potential on the web, but also we're also monitoring Drake's and the famous ones. So we have a lot of information from the Next Big Sound company, and then these radars allows us to detect music that are up and coming, and that we should also ingest it. But what's the problem when we have this kind of curated library, or from a full ingestion database, try to curate it semi-automatically with human expertise and machine learning or some clever algorithms? There's some problems that I would like to pose here and then see how we help solving them. So once you have like over 55 million songs, the problem is like there are a lot of artist imposters or people that want to trick the music industry or the system in order to get some money out of it. So there's actually that's from yesterday, Music Business Weekly article that there's some discussion about Spotify and some artists there that apparently are not real. But the main goal here is like, how can we help detecting these imposters or artists that are really, they're just, for instance, this example, the Hit Crew, this is like a band that they have like hundreds and hundreds of releases that actually, they're cover bands, but like not really good quality. So the problem here is how can we leverage the information we get from the curators in order for the machine learning algorithms that understand that this is a fake artist, and then we should not automatically be ingested into our catalog, but like surface that content into the curators or the experts, and then they can listen to this music, and then they can figure out if we want to ingest this music or we decide that that's not worth to have it. So it's kind of a similar problem that we face. It's that there are a lot of duplicated artists. Unfortunately, there's a lot of artists with the same name. Probably back back then on like this, they're from the 70s. Back then there was no Google or way to figure out, I want to name my band, like is this name already used before? So there's a lot of duplicated artists. So the problem here is like, how can we detect when we get this ingestion, like thousands of releases every week? We got like 3 albums from Bad Company. Which one of these, at least these 2 or potentially these 3 artists, the release, which one belongs to? We need to kind of disambiguate this and assign the right release to the right artist. So for this, of course, the experts can do some of that, but we have some approach leveraging the next big sound data and external information where we can, for each release that we have, we know whether, in this case of the duplicated artists, we know like that in all these releases belong to the same Bad Company artist, but the blue ones belong to different one, even with like acronyms or like nicknames. So we can just separate that. And the way we do that is with some trained machine learning algorithm that give some positive examples about this and negative examples, and then try to learn and separate the different type of artists or releases that belong to an artist. That's really important because what we want to do is, when you're searching for content, what you want to do is to avoid search clutter or noisy results. So another problem that we have that we need to solve is when you're searching for content, in this case, that's the Pandora example, when you search for all-time rock and roll, what we want, and the curators help a lot, is to have what we call the canonical version of this song. In this case, you cannot really see it, but like behind the avoid, it says like top hit or the Mortal hit. So we just provide, most likely looking for, that's the canonical version of the song. And then there are a few other examples, like cover versions or other bands that play the same song. So in order to do that, again, we need to train an algorithm that tells you, and based on popularities usually, we need to train like, okay, which one is the canonical version, which one is the listeners or our users are listening to more often in our Pandora application on the system, and then we try to separate and try to find what's the more representative version of a song. If we don't do that, the problem, like in our services, is that you search for the same query and you get like hundreds of results, and it's difficult to separate what's the relevant result that you're looking for. So these are some problems that we try to help the curators. The main idea here is that they cannot do all this by themselves because like thousands of releases every week. So we just process first all the easy examples, and then whenever there's any doubt or the algorithm is not sure whether that's the right solution, we just surface all these difficult examples to the curators, and then they can focus on each one and do research and decide what to do next. Curators also, of course, curate content. So actually, some of the most popular stations in Pandora are curated content. So they are experts that they create playlists, and they know which song is a good fit for R&B love songs or for like classic rock. So this curated content, what we do here is a mix of expertise from the curators, but also the machine or the algorithms learn from the examples that you added on this 90s alternative. We have like, let's say 20, 40, or 100 songs that the curators added there. And in order to keep the station fresh and play content all the time, what we do is like we learn which attributes or which features are good fit to add songs into this 90s alternative. So the machine learning, what it does is to provide other songs that could be added into this playlist. So instead of having like 20 or 100 songs manually selected by a human, what we have is thousands potentially of songs. So the idea is like when you click at that station, you can listen for hours and hours. And that's the idea where we learn from some examples that the curators have added in that station, and then we try to understand what's common into that playlist, and then we can add more content automatically. And of course, if they don't like it, they can thumb down, or if they like it, they can thumb it up. So we can also surface or propose songs that the machine selected and tell the curators, hey, we added this song, we think it's a good fit. A lot of people are thumbing up, and then they can just, oh yeah, actually that's a good song, and they can add it like officially there. Once we have this created content, the problem is like, how can I search for the right station for me? So what we do is, now the machine or machine learning approach, what it does is personalizing the content. So again, I present that like on the first slide, like the introduction. The idea here is that based on my music interest, it just filters all these thousands of curated content that we have, and then based on my profile, based on the type of music that I like, it just recommends and actually personalizes and recommends a few stations that I might like. So to wrap up the first part of the music curators and how we can help them into doing their work more seemingly easy, they focus on curating the catalog and making it more clean. We think that's a competitive advantage versus other services that is more cluttered and more difficult to find what you're looking for or actually listen to the music and the versions that you want. They also curate a lot of stations that are more general purpose, but then we also help and personalize this content like for you, and we tell you which songs you might like for that station. And of course, the idea of the machine learning workflow is to facilitate the work that they do. So that would be the first part. Music curators, they kind of clean our catalog. Then the second part is the music analysis. So once we have all this content ingested, we need to analyze and listen to all these songs. That's the Music Genome project. So the music analysis team, what they do is carefully annotate one song at a time. That picture is probably 3 years old, but the team now is like 35 music experts or actually musicians that they spend a lot of time listening to songs, like 5 to 10 minutes per song, and then filling like a lot of detailed information about each song. The nice thing about that is that we can learn from, once you have millions of songs annotated by experts, what we can do is learn from this and then apply what we call machine listening, where the machines can automatically listen to a song and predict what type of music is that, how this music sounds like. So to do that, I'll play a music excerpt. Let's see if it sounds. So I'll present this example of James Bay that sounds like this.
How we gonna move together? Just come closer.
So what we have here, first is all the human annotated, like the experts. I won't go into a lot of details, but like we have all the instrumentation, have like actually 450 attributes that describe each song. So we know that this song has a lot of strings, prominent string, has some acoustic guitar. We also know the type of the vocals from James Bay, which is like breathy and gritty type of vocals. It's a male versus a female type of voice. We know the rhythm of this song, which is like a 12/8, which is kind of a vals 1 2 3 1 2 3 vals feeling. So we know everything, the chord progression, the type of, it's a minor key. We know everything about this song, anything that you can imagine. So what we do here is leverage all this information that we've been collecting for 17 years and apply machine learning on top of that. So we can predict, given a new song, because we have like thousands of songs coming weekly and new releases. They cannot annotate them all. They annotate the more relevant ones, the more important ones, but then we let machines to also annotate the rest. So machine learning, that's the general framework. What mainly a machine learning black box, if you want, does, in this case it's called supervised learning. You extract features from the audio, extract some features, but the same for if you're doing video extraction or natural language processing or text. The idea is that you extract some features from your corpus. You have a lot of label examples that tells you that's a female vocal, that's a male, that's a gritty, that's acoustic guitar. So you create a model per feature, and then we create this machine learning model that it's trained by label examples. In our case, the humans have been annotating millions of songs, so we can create a model for each of these 450 attributes. Once we have this model created, we can just classify or predict the values of a new song. So when a new song comes, like Move Together from James Bay, if a human hasn't analyzed it yet, what we do is we run this model for that piece of audio, and then we can predict how it sounds like. Actually, so that's the general machine learning approach. You extract features from your domain, audio, video, text, advertising, marketing, anything that you can imagine. You extract features, you have some label examples like positive or negative. You train a model, and when there's like new instances or new examples coming, you run it through the model, and then you predict. I think that's a soft acoustic song with a male singer. So that's machine learning in general. The machine listening approach that we do, it falls into the same framework, but the idea here is like, given the MP3 if you want, or the audio file, we extract some basic features, and what we apply here is, well, this black box called deep learning that can predict features. So how can we predict this? How can we predict that that song is folk, acoustic guitar? Because what we have is this data collection from the music genome, or we have like millions of songs annotated that give you all these labels, and then this machine learning, deep learning model. For each of the models, it just runs this acoustic feature extraction. It has learned how a male vocal sounds like, how acoustic guitar sounds like. It has created a model of piano, of everything, and then it runs this model for this new audio, and then it can predict a lot of features. That's kind of ideally, in practice, let's see what it really predicts. That's the same song, the James Bay Move Together, the machine listening. On the left side, there's a lot of attributes, probably cannot read it, but it's not relevant. On the left side, like 0 means probability of, actually on the x-axis means like probability of this feature it's present or not. So on the left, 0 not present, towards 1, it means that it's really predominant. So what the machine listening, among other things, what it could predict, clearly that it's like a male vocals, this triplet or 1, 2, 3 balls feeling that I tell you about the rhythm. There's acoustic guitar, there's some bass, but also it thinks there's some mandolin there, which there's not. So actually the machine listening is not as accurate as humans, and sometimes it adds some noise. So just telling you that I think there's a mandolin, but no, maybe it got confused with some acoustic guitar sound. And it predicts that the genre of this song is folk and some folk country, and it's mainly acoustic. There's no electric guitars, or isn't like hip-hop, rap, or other produced, like more synthetic type of song. So to wrap up this second part of the genome, the music analysis, the 4 main takeaways is that you need to think when you have a corpus like us that we've been curating and annotating for 17 years, that's really a unique, it's a competitive advantage for us. Like no one else in the world has anything similar. But once you have all these songs annotated, the nice thing about Pandora is like music never stops. Like we can play, we can start a station now and like play it for hours, for days. We have a lot of options on songs to play. So we can also provide discovery through this analysis. The nice thing is like when all this new music is coming, how can we recommend new music to the users? Because there's like 1,000 releases coming this Friday. Out of these 1,000 releases, how can I recommend you the ones that you might like? How can I tell you there's a new release from James Bay that Oscar might like? So by applying this description of the music, we can alleviate or try to avoid the coaster problem, which in a recommender system, it means like you're adding new books in Amazon or movies in Netflix, and in order to know what's this movie about, you need to understand or process it somehow. In our case, because we annotate semi-automatically all these songs, we know that from all these 1,000 releases, you might like these 10 releases that sound like your profile or that you might be interested in. So we can also alleviate this coaster problem and recommend you things to you right away without waiting that people thumb it up, or without waiting that you need to purchase it on Amazon to collect user information. So that's actually very interesting. And of course, humans way better than machines to annotate carefully the music, but machine listening, it allows us to scale to millions. So yeah, we've seen the music curation. They clean the catalog. We help them with complicated edge cases with like fake artists, etc. The music analysis, we can annotate all the songs and have carefully annotated them. Then the third part is the algorithms. So how can we play songs at Pandora, and how can we combine all this knowledge in order to play like, the perfect song for you at the right time? So What we have at Pandora is what we call an ensemble recommender, or imagine like an orchestra with a lot of musicians, and then there's a director that orchestrates and directs the whole orchestra. So what we have actually is an approach that is called content-based similarity, or based on these approaches or these algorithms leverage all these descriptions about the music. So we have millions of songs annotated, and we can find that because you like this song, there are songs that sounds like, has the same feeling like James Bay. It's a slow song, has acoustic guitar, etc. So we can find similarities between other songs. So we have a lot of approaches that use this content-based similarity or recommender system. But we also use a lot the collective intelligence or collaborative filtering, which allows us to mine all these 80 billion thumbs that we've collected from all the users. So once you have 80 billion thumbs, you can think of a matrix where you have all the users and all the songs, and then you can put values like Oscar has thumbed up all these songs, so you have all this information in a matrix, and then you can process them in order to find similarities based on the user, the explicit user likes and dislikes. So content-based is based on how the music sounds like. Collective intelligence, we aggregate all the knowledge from all the users, and it's based on the preferences of the users, what they like and what they don't like. And then the third approach is what we call personalized filtering, where it's based on your information, based on your thumbs, based on your demographics, where you live. So based on all that, we can create a station that is tailored and special for you. So as I said, altogether we have over 70 algorithms. So we have this ensemble recommender or director that just asks all these 70 experts, like, hey, which song should I play now? I'm on a James Bay station. You just thumb down Mumford & Sons song. What should I play now? So this director asks all these 70 experts, and then in 20 to 50 milliseconds, each of these 70 experts, some coming from human experts, curators, some from machine learning, complicated models, they recommend you, hey, maybe now you can play this song. So we get like 70 recommendations from all these experts, and this director try to see what's the right song to play for you right now. So if there's like 5 models that agree that now it's a good song to play, like a U2 song, then most likely we'll pick that song because there's a lot of agreement between the experts. And that's how we can select the next song to play for you. This slide is mainly, if there's anyone interested in the technologies that we use, but I won't go into a lot of detail here, but like we've been using a lot Spark and Scala since the last 2.5 years. Of course, we use a lot of Python stuff and Hive to process all the data. And then at the top, on the real-time recommendation, we have all the system is built in Java. We have Redis and Memcache to load all the information, all the models from the user, all the models for the songs. So it's easy, like in real time, in 50 milliseconds, you can recommend things to our users. So the top is more like the online recommendation or the online system, and Python, Scala, and at the bottom is more like the offline processing. And in order to process 80 billion thumbs, it takes some time, so we do that every night. We have a model that runs every night. And then next day, it has the model improved or updated. So I presented like the 3 parts: music curation, analysis, and algorithms, but of course there's Pandora. And so who's Pandora? All the users, all the 76 million users that uses Pandora monthly. So what we do also is that we play around or fool around with our user, and what we do here is called A/B testing, or we test our new algorithms or our new interface or anything that we do. We present it to our users, and then we see how they react, if they like it or not. So this idea of A/B testing, which the main idea of A/B testing is that you have a treatment group of users that they see a new version of Pandora, and you compare with a control version of the users, a control group of the users that they see like the old Pandora without that new algorithm or this new way to play music or new way to play ads, recommend you ads or like play you ads. So in this A/B testing role, what we do at Pandora is offline. We have, all the music history for all the users for the last 10 years. So we can, if we have a new idea, a new algorithm, first we test it offline. We grab all this information with Hive and blah, blah, blah. So we have a lot of information. We create a model, and then we run it with past historical data. It's called offline. And then we can see precision, recall, a lot of values to see whether this algorithm makes sense or it's a disaster. if these offline results look good, then we start to this online testing when we experiment on 1% of the users or 5%. So this 1% of selected users, what they will see is this new version of Pandora with this new algorithm. And then what we will do is measure, do they like more the songs that we play there? Do they thumb up more or skip less? And then we run this for months, actually. And then we measure and see if there's any statistical significance between the treatment group and the control group. And then if everyone likes it, we start with 1% of the users, 5, 10, 20%. At some point, like everyone is experiencing or enjoying this new version. So we're the humans. So we use that with we have hundreds of, if you use Pandora, most likely now you're on a experiment test, like we have hundreds running all the time. But before we go from the offline to the online, what we do is internally have some quality control where these experts, the music curators, or even myself, or people that like music, before going into the online and test it with the users, we have a website where you can test this experiment and see how it sounds like. So because sometimes there's an algorithm that you think it works fine, but we want users to, even if like 20 to 100 users at Pandora or internal employees, experts use that, we want to make sure that we didn't screw up or we didn't play bad music. So we also have the human experts here that beat or tells us, well, now it's ready, this offline experiment is ready to go online before we if there's any bugs, sometimes there's bugs, like we try not to expose that to 1% of the users, which is actually almost 1 million, 1 million users might be experiencing this bug. So we have this lot of quality control where humans interact with that new version. So in terms of the metrics, so when you do A/B testing, what you want to do is to compare whether the experimental group or the treatment group are doing better than the control group, that the one that doesn't have this new Pandora version or new algorithm. So the metrics that we're focused on is to avoid churn. We want to measure and we want to make sure that people are coming back to Pandora, so the users are not churning. And this A/B framework that we have, it shows us all the differences in terms of active users. Are they more active? Are they coming back daily more often? Or are they spending more hours? So the main metrics that we focus is to avoid churn, that they're not leaving, and then that they're a sustained audience, that they're come back and they're coming more often to Pandora. So more concretely, the metrics that we have in terms of retention, we measure, we have like probably 50 or 60 metrics, but the ones that are relevant is like time spent listening because of this new algorithm or this new version of Pandora that we expose to the treatment group. Do they have, are they spending more time using Pandora? Are they coming back more often? Or the active days, they're coming more often? Or also we measure the activity. Are they summing up more or less? Are they skipping less? We also A/B test all the ads supported, like for everything with the ads related, we also A/B tested. So we want to check the click-through rate of the ad, if they're more engaged or less. If we personalize an ad, then we want to see if people are more engaged with that ad or not. So these are the metrics that we focus on, and then if everything looks fine, we measure that for months, and then we increase the exposure group from 1, 5, 20% till we roll it out to everyone. So with that, I think I have 5 minutes left. I would like to just wrap up this presentation with a few takeaways. So some of the lessons learned in this human in the loop and machine learning. This one, it's probably very naive, but it's important to insist on that. So human experts, they excel at quality, they have domain expertise, they know exactly this band that recorded this album back in '99 and they're from San Francisco, but no, they're slow, they cannot analyze 55 million songs or 500,000 artists. Whilst machines, they really excel at quantity, but they're kind of naive or dumb. They don't know exactly what they're doing unless you teach them to not be naive or dumb. So one of the goals, interaction between humans and machines, is like humans or experts need to teach AI or ML to not do stupid things. And we have a lot of examples here that I can tell you that we, or my team, the scientists, did some not so smart things, like playing AC/DC Highway to Hell to a Christian rock station. We did some of that, and people didn't quite like it much, especially that audience. Of course, it makes sense. So you need to protect. You need to, if you have like a In my case, I'm sharing my account with my son, so I have Social Distortion and Green Day, but also I have Disney and other stations there. You need to make sure that when he's listening to a children's station, like there's no explicit content, or there are no like offensive lyrics, or the album cover is the right one. So all these, you need to kind of train the AI or the ML system to do that, because else they will, people that like Green Day also like Disney songs. Well, we're just share account, but just process everything, and then it sees some similarities, or sometimes there's some things that, because the machine learning has been trained with zeros and ones and no really context, you need to train and teach this model. And in the end, you need to add domain expertise into this black box so they don't do stupid things. Also very important is that you need to build the right tools where machines can do the easy repetitive tasks, but especially help experts to find the needle in the haystack. So the idea here, as I repeat before, is that machines can do all the easy, like bulk reading a CSV or a spreadsheet of 10,000 rows and just process them. In Python, you do it in 1 second. But then if there's like 100 cases where like the machine is like, I don't know if that's the right thing, or that's a duplicate artist, or that's a fake artist, then just when in doubt, what you would do is like you would process everything, and just the more complicated cases, we pass it to the experts, and then they focus on these concrete examples. So what we're trying to do at Pandora is like that. I mean, we use spreadsheets a lot, but what we don't want is that experts give them a list of 2,000 rows and then go one by one and process them, and because that's very time consuming. What we're always trying to do is help them with machine learning to pre-process the easy basic cases, and then just try to give them the more interesting cases for them. And I'm almost done now. The learning from the users, the A/B testing, like the treatment group and the control group, is very important, because we can see daily improvements in the system. We have all these metrics that we measure every day, so we can see like people are more engaged, or we can see people are less engaged. If we play AC/DC Highway to Hell to Christian Rock Station, we have an A/B test running. Like the next day or in a few hours, we'll see like thumbs down or increasing a lot. We'll see the difference between the treatment group. They're thumbing down a lot on that station, so we can really easily detect WTF or like bad music. So and then we can improve the next day. The nice thing about A/B testing is that you can measure everything and see the user satisfaction. And once you have all these measurements and all this information, you can make informed decisions. Like I can go to the CTO and tell, hey, we should try this and this and that. We've been running for 2 months, and we see that has a value, especially for the ads or more marketing, or more when you need to make decisions about investments. Like you can prove or tell them, I don't think that's the right thing to do. We're playing too many ads, and that's people are churning. So we can make all these informed decisions based on how the users interact with the system. So just to wrap up, there's a lot of controversy. It's only humans, it's the machine. It's like so our approach at Pandora is like it's not really one versus the other, but what we see is like the combination of humans and machines, and what we like to tell. That our approach is a mix of art and science. So with that, thank you very much, and that's it. I don't know if I have time for questions. Well.